Continue a little bit more in learning about transition metal catalyzed reactions. We started with palladium catalyzed reactions. We learned about the Stille and the Suzuki coupling. And the last reaction we looked into a little bit further, which I just would like to recall here, had been the Heck reaction, a reaction that allows you to start from an aryl or vinyl halide or triflate, couple this with an alkene, palladium zero catalysis, to arrive at the cross-coupling product here. Now the question is, can we do an analogous reaction using, instead of an alkene, using an alkyne? And in fact, this is working, and this is working even better than the Heck reaction is. Alkynes are much more reactive in this type of process than alkenes are. However, the reaction mechanism and the reagents we are going to use are a little bit different than in the Heck reaction. The reaction I introduced to you now has also a name. It's called the Sonoga-Shira coupling. And the difference in this reaction is that you need palladium zero as a catalyst, but the other catalyst you need is a co-catalyst, and this is copper 1. What you make use out of the reactivity of alkenes is that alkynes are relatively acidic. If you consider the pKa of an alkyne, this is around 25. Compare this with 35 of the CH of an alkene. And the acidity of alkynes is sufficient that copper iodide, for example, so that's a common salt you are using, copper 1 iodide here, is reactive enough to form the cuprate of the alkyne. So Hi is taken out here. Again, as we have learned in the Heck reaction, the forming acid is neutralized by adding into the reaction mixture an amine. Same thing we did already here as well. And now again we have the type of mechanism that we have seen with the Stille and the Suzuki coupling. Because now the palladium zero will do the oxidative addition. So here we have palladium 2. Here we still have copper 1. And these two will now react in the very same or analogous way like the Stille or the Suzuki coupling is working. These two species will undergo a transmetallation. The very soft palladium center will take off the soft carbon ligand here, and the harder halide will combine with the relatively to palladium more harder copper atom. And so in the transmetallation step, we will form this species plus the copper salt back. And you can see here, this is the moment already when our copper 1 catalyst gets regenerated. And this species, palladium still in the oxidative state of +2, will now undergo a reductive elimination. Palladium 0 is extruded, regenerating the palladium catalyst now. Forming the cross-coupled product. And I don't know if you had already the chance, probably not in the advanced lab class, to run such a reaction. These reactions are really lovely. They're sometimes over in 30 minutes. You mix all the components, your halide, your alkyne, palladium 0, copper 1, and amine. You mix everything together. You wait. You can very often see that the reaction is exothermic, and it is over very rapidly with very low concentrations of catalyst. So often 0.1 to 1 mole% both in copper and in palladium suffice in order to do this reaction with virtually quantitative yields. So that's a very, very nice reaction. And what you can see here is that it allows you to rapidly build carbon chains here, because you can add alkynes. Keep in mind, we can reduce alkynes either to the alkenes, both cis and trans. We saw the 2 types of palladium catalyzed hydrogenations. You can reduce it to an alkane by, again, palladium catalyzed hydrogenation. And so basically you can use this reaction to build molecules quite nicely. Because not only that you can, if you have already your alkyne here formed, then you can add another, a second substituent here to make the disubstituted alkynes. The reaction works. You can start with, in principle, you can start with acetylene and do 2 Sonogashira couplings left and right in order to build up the required carbon atom you need. Now, acetylene, as you all know, this is not necessarily a chemical you would like to work with in the lab. It's a gas. You have to be extremely careful that you don't mix it with air and then somehow get ignited, because it will widely explode. But there are acetylene equivalents. And the one equivalent which has become very fashionable is trimethylsilyl acetylene. This is a liquid. And now what you can do is you can do your first Sonogashira coupling to build the silyl substituted alkyne. And now there are various ways to take off a silyl group. For example, most commonly you can use fluoride. You make use that the silicon-fluorine bond is the strongest one, which we know. So now you create your alkyne and do a second Sonogashira coupling now with a second type of aryl or vinyl halide, whatever you need here, and then this way create the acetylene you need. Now, trimethylacetylene has one disadvantage. Not so much for us in Bavaria, because in Bavaria we are lucky to have a very major chemical corporation here, which is Wacker Chemistry. And as you know, Wacker Chemistry is the leading manufacturer in the world of all types of silicon compounds. And among them, they also produce trimethylacetylene. And if you, at least we here in Bavaria, if you give them a call and say, would you like to support poor academic researchers, they will give you this chemical. However, it's expensive. There's a second compound which you can use, and this is very, very inexpensive. This looks a little bit strange in the first moment. And this is this compound. And again, it's a monosubstituted acetylene. You can do the Sonogashira coupling in the very same way as I have shown you. And note that a free hydroxyl group does not hurt this reaction. So protic sources are compatible with both of these catalysts. And so you will form this type of coupling product. And you might already wonder how this compound is made and why that is so cheap. The reason is this is a coupling product of acetylene and acetone. And you can reverse this process by treating this with a strong base, and you make use out of that that acetylene is quite acidic. So actually an acetylide can be a leaving group. And under basic conditions, acetylene can be extruded. So you treat this with a base. And then via the acetylide, which gets protonated by proton source, you form acetylene and acetone. Acetone can, of course, be very easily removed by evaporation. So this is a very, very good alternative to trimethylacetylene. And if I recall it right, it's like a gram is €1 or something like this in that range. And this is, I believe, is 20 times as expensive, at least. Okay, so this is a useful reaction. And this reaction has been applied in all types of pharmaceutical syntheses to make drug molecules, but it's also been applied quite a bit in material research. And especially in electronics, because you can make highly extended conjugated pi systems this way. And let me just show you one example, which was probably not used for electronic purposes, but just to show you how well this reaction is actually working. This is an example which was, I believe, discovered in the 80s already, or reported from Professor Vollhardt, 1986, and he showed actually that you can do these type of reaction multiple times. For example, you can exchange in hexabromobenzene, you can exchange all bromine atoms for such an acetylene group. And then in the second step, the trimethylsilyl group was taken off. And so you can make such highly unsaturated systems. You can extend this to make further highly conjugated systems this way. And people are looking into this, for example, in material research to make organic conducting materials. So it's a good reaction. Nevertheless, I believe here total yield had been 28%, where you might say, that's a little bit low. If you calculate the yield for each carbon-carbon bond forming step, that's of course a lot better. And one of the problems you have here is of course separation. If the reaction works 5 times well and the 1 times it doesn't work, you can see that you form mixtures, and you also lose certainly a lot of material by purifying then your hexa adduct against penta or lower type adducts. Okay, so that's good way. And now let me show you one example where we will have 3 palladium reactions in one pot, 3 different ones. And also should show you the power you have with these type of coupling reactions to build up rather complex molecules. And you will see that we are doing a Heck, Stille, and Sonogashira coupling all at once. And so the example which I would like to show you is starting from this vinyl dibromide here, which has an acetylene group in vicinity. And this was treated in the first reaction step with this palladium 0 and as a coupling partner in a Stille type reaction a tributyl tin compound of that acetylene was used. So when this reaction is being carried out, as a first intermediate, an intramolecular Heck reaction is occurring. So first, before even the Stille coupling takes place, intramolecular Heck. And that this reaction works in this way is not obvious. Because look what is happening here. We have 2 different bromides. And apparently, what is happening here is that this bromide here is reacting. And then it's doing a ring closure. And then 5-exo Dick manner. And of course also again in a cis manner. So this bond and this bond are formed by the cis addition. But the one thing you should wonder is, why is this bromide reacting? Why not this one? So apparently this one is more reactive. And at least if you look at this vinyl geminal dibromide, there's no real good reason for this. And again, that's a detail, but nevertheless, I want to show you simply this example, not for, again, not that you memorize it, but that rather similar substrates can have can have reactivities that are different enough that indeed selectively this vinyl bromide will react and not this one. And I don't have a good explanation here, but a reasonable cause I could create here is that the triple bond with the highest electron density in this molecule, that the palladium will pre-coordinate with this. And then, of course, in order to do now the oxidative addition, this bromide is accessible, while this bromide would be too far away. So I believe this is the reason why we see this type of selectivity here. And so from this intermediate, now the Stille coupling will take place. So again, I draw the substrate here. And now after that reaction was completed in the same flask, we still had palladium 0 in the pot, of course. Copper 1 iodide was added to set up the Sonogashira coupling. And as a coupling partner, was used this compound, which I've just shown you as the equivalent of an acetylene. Too small here. To set up this reaction. And this is an intermediate in a class of compounds, enediene cytotoxic compounds, which are very potent against cancer, although they are so potent and so toxic that so far no drug of this type has been brought to the market. But very few steps here will convert these type of intermediates into these respective compounds, and it has been recognized that these type of unsaturated enedienes are very potent in order to interact with DNA molecules and actually cause DNA cleavage. Should also, you have in your handouts, you have the literature. This example, the full reference, this example again comes from a Japanese group. And you know that if you ever want to read the full articles on this, it's very easy. In the handouts is the full literature citation, and you can easily access this through our electronic library. All right, so what we did so far is that we learned about reactions which will form palladium-catalyzed carbon-carbon bonds. And this was always believed to be the most important type of reactions. However, you might wonder, what about forming carbon heteroatom bonds? Is this something which would be useful? And is this something which can be accomplished? Let me show you an example of a reaction which might interest you. If you have a benzene and you would like to do a nucleophilic substitution with an amine, in order to form the corresponding aniline. I guess you have a feeling how this can be accomplished. So this would be a nucleophilic aromatic substitution. But as you know, is that arenes itself are actually have itself high electron density. In fact, usually aromatic systems react with electrophiles. They work like nucleophiles itself. Only if you have enough electron withdrawing substituents, then nucleophiles can attack here and do this displacement. Or the alternative is that you treat this under very harsh basic conditions, sodium hydroxide, to form as an intermediate the arene, which then can add the amine to form the corresponding aniline. And besides that, in this type of reaction, we use very harsh reaction conditions. There's, of course, another problem that you have 2 points where the amine can attack. And so if you have substituted aromatic starting materials, you might form mixtures. So clearly, this is not a very useful reaction. And you know that usually when you make anilines, what you would try is you would do a nitration and then do a reduction. This is the more common way to functionalize aromatic compounds towards anilines. Now, anilines are an amazingly important class of compounds. They are important to make azodies, classical process to convert aniline by diazotation into dyes. But also, this type of structure is extremely important in pharmaceuticals. And there have been many drugs are on the market which contain this type of structure. And so obviously, if you have a highly functionalized starting material, this is not the most attractive way to introduce then an amino group. Nitration, where you take concentrated sulfuric acid and HNO3, is also not the most attractive way to do this. And so the question is here: is there an alternative by doing a palladium 0 type process? And indeed there is, which now also has a name. This is the so-called Hartwig-Buchwald reaction. And in principle, it works. Doesn't have a T here. In principle, it works very analogously to the Heck reaction or other coupling reactions we have seen. And you might wonder why it took so long that this type of reaction was discovered. This came almost 20 years or more than 20 years later than the other coupling reactions were come. But it took, nevertheless, although the mechanism I show you in a moment is very analogously to what you have seen before, the right conditions had to be found to make that type of reaction work. So the overall process, which had been developed is that you use a palladium zero catalyst. And although we haven't really gone into this too much yet, I should point out that for convenience, you can use palladium acetate, which is a palladium 2 salt, as well, because under various reaction conditions, either by solvent or also by ligand, for example, triphenylphosphine will rapidly reduce palladium 2 to palladium 0. It makes triphenylphosphine oxide. So the phosphine gets oxidized and palladium gets reduced. So palladium acetate is more easily to handle. It's air stable and so on. So that's very often why you see that a palladium 2 source is being used, but the catalytic active species is always palladium 0 here. So you need a ligand for the palladium. And without really going into any detail, but this was one of the tricks why it took long that this reaction was discovered. Simple triphenylphosphine is not working in this reaction. Sterically more hindered phosphines like this DT-butyl and then biphenylphosphine. And again, don't memorize these things. But nevertheless, this was the key that this reaction is working. And the other thing which is also important is that you need to use a base here. As we have seen in the Suzuki coupling needed a strong base. The same is true for the amination reaction as well. And then this way, under very mild reaction conditions, room temperature, you will create the corresponding anilines. And again, compare that to the other ways, concentrated sodium hydroxide heat, or doing a nitration with sulfuric acid. Clearly, this is by far a superior and much more easily to run, and of course, much more tolerant process, because this type of coupling reaction tolerates just about any functionality you might have present. Now let's look at the mechanism. So the aryl halides here in this case are the compounds which are usually used. Vinyl halides, I'm not really aware of it. And the first step is the step we always know, and again you have a ligand here, so ligands might be coordinating here as well. And now in principle you can see what has to be done. When we had the Heck-type couplings, Sonogashira couplings or so, we would exchange the halide for carbon substituent and then ultimately do a reductive elimination. Now, very simple here as well, right? All you need to do is you exchange the halide substituent for the amino substituent, and an amino group should be a good nucleophile. And then do the reductive, and then reductive elimination could occur, and you are done. So in principle, this seems to be very easy, but nevertheless, the direct displacement with amines has not been working, and this is where the base came into play. It's been recognized that you need basic conditions, and it has been postulated that first an exchange with the alcoholate group will take place, which only then is being displaced by the amine to form the T-butanol. And now you can see what you're achieving. You are getting a deprotonated amine, which is of course extremely basic, as a ligand onto your palladium fragment. And as it appears like you have to go stepwise from the softer to the more harder ligands here, and this is why you need it as a mediator at the base in order to make that process work. And then once you have this, the normal reductive elimination takes place, of course driven by the very stable carbon-nitrogen bond you're forming here. So again, you should recognize that this is, of course, thermodynamically a favored process. You're exchanging a carbon halide bond, especially when it's bromines, but I've shown you that it's also working with chlorines. You're exchanging this for the carbon-nitrogen bond, and at the same time you're forming here again the HX by elimination, which then again gets neutralized under these basic conditions. Okay, so this is a reaction which is now heavily used in industry, maybe even more than the carbon-carbon bond coupling reactions. And so it's if you later start working in an industrial company which deals with synthesis of organic molecules, might be a good way, or might be very good to keep this very important process here in mind. Okay, I would like to show you another palladium catalyzed reaction, which is again a very useful, versatile type of reaction. You will see that the mechanism of this reaction is different. So what I like to show you is the allylic alkylation type chemistry. And this is also palladium catalyzed. Again, to be more specific, it's again palladium zero catalyzed. What is the type of reaction I would like to show you? It's the basic, the minimal structure we need here is an allylic system with a good leaving group. And acetates are the most often used type of compounds, but also here halides have been used as leaving groups. Carbonates, and a couple of more. But acetates are very common and very useful. Think about this. Allylic alcohols can be synthesized quite easily. For example, reduction of an alpha-beta unsaturated carbonyl compound. And then if you convert the alcohol group in an acetate group, treating it with acetic anhydride, very, very easily you can arrive at such allyl acetates. And such type of allylic acetates, of course, undergo nucleophilic substitution. By either attacking on this carbon in an SN2 type fashion, or attacking this carbon in an SN2 prime type substitution reaction. And this reaction works generally well, especially with good nucleophiles. However, if you have weaker nucleophiles, and especially if you have carbon nucleophiles, for example, a very commonly used C nucleophile are stabilized anions like the sodium anide of malonic ester, which you know from malonic ester synthesis, of course. And these type of C nucleophiles will not readily react with such allylic acetates because they are not reactive enough. Then there are many other nucleophiles, of course, with heteroatoms, NO, S nucleophiles, phosphonucleophiles have been used. In principle, also hydrides can be used. So as a nucleophile, you would use H-, which can be borohydrides, tin hydrides, aluminum hydrides, and so on. So all these type of nucleophiles, in principle, could facilitate displacement on these allylic acetates itself. However, it was recognized that in the presence of palladium zero catalyst, this reaction is greatly accelerated to the point that with some nucleophiles, which would not react in the absence of a palladium nucleophile, you can get the reaction to work. And moreover, you can use much milder conditions, and the reaction is much more faster in the presence of the palladium catalyst. The other thing which is recognized if you use this type of palladium catalyst is that you can control stereochemistry much better. I wonder if I show you the example or if I show you first the mechanism. Let's maybe start with the mechanism of this reaction, and let's start on a very classical substrates where stereochemical issues can be looked at very, very nicely. So what we have here is we have an allylic chloride. We have two substituents here which are cis to each other. And what will happen now if this is reacting with palladium 0? Now, from all the previous reactions we have seen is that into a carbon halide bond, palladium will undergo oxidative addition. And in principle, this will also occur here. However, in this case, the double bond here in the allylic position will coordinate first with the palladium and assist the overall oxidative addition. And the way you should think about this is that what palladium is doing in this case is really reacting like a nucleophile. We have never really talked about the exact mechanism of the oxidative addition. But one way to look at this is that palladium 0 is a nucleophile and is simply displacing the halide here. And this picture is especially useful here because what one believes is happening is that the palladium coordinates with the double bond in order to do in a nucleophilic type substitution the extrusion of chloride. And an SN2 type process is, of course, undergoes by backside attack. So the first important realization is that the palladium will approach the allylic system trans to the leaving group here. So this is the typical SN2 type reaction mechanism. So again, keep in mind here, the oxidative state of palladium is still 0. At this point, only coordination takes place, but no oxidative addition has been taken place. But now in the next step, the oxidative addition takes place, and a palladium allyl complex is being formed. And this is a very stable affair here. So now, again, formally, palladium has undergone the oxidative addition. It has the oxidative state of +2 here. And formally, we have an anionic ligand here now created. And now these palladium allyl complexes will undergo nucleophilic substitution. They will do this in principle in two different ways. A nucleophile can now attack this allyl complex externally and displace the palladium here. Now again, the nucleophile will do this in an SN2 type fashion, so it will attack here opposite to the palladium fragment, so it will come from the top. And therefore deliver the nucleophile as shown here. So basically we have an inversion here. We have another inversion here. And so overall, you have a net retention of stereochemistry here. Now note, of course, that in this example, the nucleophile could have had also attacked from this side. Which then should have given us this product here. I hope you realize that in this case, these are enantiomers here. So if you would have started with an optically pure material here, you would have generated, in this type of reaction, a racemate. If you would have started with a racemate here, so rather than having just this chloride in here, also having the enantiomer present, and as you probably can imagine, this is to synthesize such allylic chlorides racemically is much easier than doing this in an enantioselective way. Again, the racemate should have provided the racemate here. However, interestingly enough, and we will not really go into this, but I just would like to point this out here. If you then do the reaction in the presence of a chiral ligand, and if the chiral ligand somehow, without, I will show you, and you have in your handouts, you have one model for this, but I do not really want to go too much in detail, but if the chiral ligand is able to tell the nucleophile, please approach from the right, or please approach from the left, however the ligand here is able to do it, but in principle it should be possible to transfer chiral information to differentiate left and right in this allylic process, then you will be able actually to create enantiomerically enriched or even enantiomerically pure compounds. Starting from a racemate here, because you go through this type of symmetrical allylic complex here. And this makes this whole strategy very, very powerful. Now let's look at another way. There is nucleophiles will give you the inversion chemistry here. However, certain nucleophiles will displace the palladium fragment from the same side. And one nucleophile which is doing this is hydride. And I've chosen here the deuterated variant, sodium borodeuterate. If you use this, again, very good method to stereoselectively introduce a deuterium atom into a molecule. However, the displacement will take place from the same side of the palladium fragment. So what's the difference here? Typically, these type of inversion chemistry, all other nucleophiles will give. So the C nucleophiles, but also the N and even the O nucleophiles, they all will give inversion, and only very small, very highly charged nucleophiles, and I guess you can see the idea here, only hard nucleophiles will give net inversion here. And soft nucleophiles will give the double inversion, which will lead to the overall retention. Now, why is this? What makes the hard nucleophile different here? And the mechanistical model which is being put forward here, and which I believe is a good one, is the nucleophile, of course, can attack this center, which is a soft center, but it can also attack on the charged palladium, which is a hard center. So this here is the soft center attack. But if the nucleophile is adding on palladium, then the hard center is attacked. And deuterate hydride is hard enough that it will first coordinate with palladium. And then you can see then of course the nucleophile is on the side of the palladium. And then in a reductive elimination, palladium will get extruded and delivers then the nucleophile from the same phase as it has been here before. So in the hydride case, deuterate will attack palladium here, displacing the acetate. And then the reductive elimination, as we have seen it many times in other type of reactions before, occurs then, of course, from the same side where the palladium is coordinated to. And forms then the product. So what you should remember is that in virtually all cases with nucleophiles, these type of substitution occurs under retention, double inversion, and only very hard nucleophiles, and hydrides are really the only nucleophile which come to my mind here, which I'm aware of work in this way, will do the substitution under overall inversion. So let's take a few examples how this reaction can make you a millionaire. So let me show you the synthesis of carbovir. This is a drug which is very promising in the battle against AIDS, along with AZT and DDT. It was developed by Merck, Sharp and Dohme in the US. And the synthesis I'm showing you is a synthesis which was developed by Barry Trost at the Stanford University. Merck is actually making the compound by an enzymatic process. But the usual battle, the question is, can chemistry compete with enzymes? Can be definitely answered yes in this case. Let me show you the compound. Very typically, these antiviral compounds look somehow like this. The idea, the mode of action is that these compounds resemble nucleosides. Which look like this, and then we have a nucleobase here. You usually know what happens is that these get built into RNA and DNA strands, depending what you have here. And so this way they can replicate. And the idea of these compounds is that they basically have a number of features which the nucleosides also have, but what they are all missing is they are missing this hydroxyl group here. So if this compound gets built in, if it is recognized as a valid building block, and it's then built into an RNA or DNA strand, it can only start getting built in here, but here it cannot replicate. So the DNA synthesis stops, or RNA synthesis, in this case, stops. And so therefore, these compounds might be able to interact, or they can interact in DNA replication. And since usually affected cells replicate much faster than healthy cells, this is a way to fight selectively infected cells, although you know that especially in AIDS therapy, side effects are quite severe because also you damage, of course, healthy cells as well. And so this carbonucleoside here has in addition the feature that it has a carbon atom here, so it's a cyclopentane derivative rather than the sugar backbone here. This gives it additional stability, cannot get hydrolyzed so fast, and so therefore it's a stable compound. Yeah, sorry, I have somehow, it was raining down here on the board. But you know, of course, always my answer. If you cannot read it and you're not sitting in first row, it's not my fault. You can only start complaining about things like this if you're all sitting in first row, or first and then second row, of course, if the first row is filled. OK, so how can this be made? Now let's look at this. You can immediately see that it has a couple of allylic functionalities here. So here, for example, we have an allylic. We have the base here in allylic position to this double bond here. And in principle, we have another allylic substituent here, this CH2OH group. And indeed, this is how the synthesis then was envisioned. Very readily available starting material. Is this cyclopentene 1,4-diol here? And note, please, that this is an achiral compound. It's a meso compound. As you can see here, we can easily put a plane of symmetry through this. So this is achiral. However, it's important in the end of the synthesis that you generate this in non-numerically pure, because only the right stereochemistry will, only the building block with the right stereochemistry will be recognized as a building block for DNA or RNA synthesis. If you have the inversed one, then the compound simply has no activity. And so what has been done here first is the hydroxyl groups have been converted to a beta leaving group. And I told you already that acetate is the one leaving group which is used very often. However, in the synthesis of Professor Trost, he used a different leaving group. He used carbamates, which you might, the structural element you should recognize when you learned about peptide synthesis for protecting amines. And so basically here the carbamates were being used. And again, extremely good leaving groups, because after insertion, obviously you can see that the leaving anion is resonance stabilized. And so therefore it can very easily undergo this type of chemistry. Now, I have in your script, I have two different types of synthesis of these molecules, and I'm just seeing here that this is not the one which is being used here. Sorry about this. You will see that here a simple acetate type of compound has been used. A simple benzoate is being used. And since in the end we would like to have the two stereocenters up here, let me just redraw this as being both up. It's still the same compound. I simply would like to do it this way. And so when you treat this with palladium 0, and if you treat this, in this case, with a nitrogen nucleophile, and you can take azides here, and rather than just using sodium azide, which I had just drawn here on the board, for organic type of reactions, trimethylsilyl azide is more preferred because it's soluble in organic solvents, while sodium azide would only be soluble in water. So you can take this palladium 0 catalyzed and by doing the palladium catalyzed allylic substitution, now in the synthesis, azide was introduced as a nitrogen nucleophile here. And now note again, when we are forming the palladium allyl complex, what should be clear right away is that the palladium has to come from the bottom. But again, what is not clear is if it shoots out the right or the left benzoate group. And in the absence of any chiral information, both of them should get equally extruded. But in the synthesis, and again, I'm not going into this, in your script is the actual chiral ligand shown. If you use a chiral ligand, the chiral information is able to tell more or less to make one displacement more favorable than the other one, to differentiate between left and right here in this case, and to form only one of the possible allyl complexes. So again, palladium is below the plane here, but in this specific case, selectively the right benzoate group has been displaced. And now when the nucleophile is attacking, please also note again that you have two positions where it could attack. And these positions, because we have another substituent here, are not equal. And quite apparently a good argument that only this is occurring is that it's sterically more favorable to attack away from the benzoate group rather than attacking next to it. And keep in mind, since it's a nucleophilic substitution displacement, which occurs now opposite to the palladium fragment, it has to come in from the top, so from the same side like the benzoate is. And so this way, this azide was synthesized in an enantiomerically pure form. And then in a few steps, which I will also not go into this is converted into carbovir. There's a lot of very interesting nucleoside chemistry out there, which you will probably learn in the next semester if you take Professor Wagenknecht's synthesis or class on nucleosides and DNA. It's quite easily to convert azide groups into these nucleobases. And what you also see is here you have to somehow extend this substituent by one carbon here, and this is also relatively easily possible. I promised you to show you one example in order to explain the concept how a chiral ligand might be able to differentiate between left and right. And I will try to do this on a very simple case, but which I think shows in a very, very nice way how such chiral induction can be done. Unfortunately, most of the cases we have are much more complicated, and we have a very poor understanding of transition states and models, but a few reactions are out there where you can actually show this nicely. And so let's go back to an enantioselective variant, and now to actually try to understand how this can work. So if you consider this allylic acetate here, which has a chiral center, we are going to start using it as a racemate. We can easily see how such compounds can be synthesized. This is a simple aldol condensation type reaction here, reduction will give you the allylic alcohol, and then protection as an acetate very easily gives you these type of compounds. So we treat this as palladium 0. But we are using a chiral ligand. And this ligand belongs to the class of aza semicorinths. You can see it's somehow half of a porphyrin type structure here. These type of ligands were invented by Professor Andreas Pfalz at the University of Basel. And there are many similar ligands around this now, because these type of ligands has become one of the most successful chiral ligands in asymmetric synthesis. And so if you do this, you will create, in the presence of a nucleophile, so in this case, the sodium salt of dimethyl malonate has been used. You will create a chiral compound which, first of all, we are again forming such a palladium L complex here. And then the nucleophile can attack from either side. And although we are using this racemically, let me give this a stereo information here. So let's say we're looking at the compound which is up here. In this way, we would form the palladium being behind here, and the nucleophile would come from the front. And let's say A or B. If it comes from the A side, it will give us this product. If it comes from, if it attacks the other carbon, it will give us this product. Again, these two are enantiomers. And if our ligand is chiral, if it has chiral information, it might be able to tell the nucleophile that it should either attack on the left side or on the right side. And how these type of ligands are able to do this, I will show you now in the, and for this we need to draw the palladium ligand complex. Let me see if I do a good job here. In the handouts you have a very, very nice picture of this as well. So this is the palladium complex which should be forming. Now note here we have two stereocenters in this. But note also that this ligand has a C2 axis here. So if I rotate this by 180 degrees, I will always get the same compound. So again, I do not have to be concerned if this part is on the left or this part is on the right, because I can always rotate it by 180 degrees to mirror to get the same molecule. So if we now have the palladium, if you have now the L fragment on the other side, then the L fragment takes up such a zigzag conformation as shown here, so that the phenyl groups have the most space, and it will coordinate like this. And in my case, I have drawn both phenyl groups pointing down. Does it matter in this case if both phenyl groups pointing out down or if both phenyl groups pointing up? No, it does not. Again, rotate this by 180 degrees, then these two would have looked up. This part would have remained unchanged because of that C2 symmetry. So no matter how I rotate this, I will always have basically this type of situation. And now let's see, how is now the nucleophile being told to attack one carbon, this carbon, for example, and not this one. And the difference now, you see, somehow this has to be related to the chiral centers which we have here. Now look at this. In our complex, one of the R groups, and typically very sterically big R groups are taken here, T-butyl or phenyl groups. Now this R group is pointing down. This R group is pointing up. Both phenyl groups are pointing down here. So there should be much more steric hindrance between these two phenyl, between this phenyl group and this R group. While on this side, there's only the small hydrogen going down here, and this phenyl group is going down here. So now you see suddenly how this more or less symmetrical, or this symmetrical L fragment in the absence of a chiral ligand, now is not symmetrical any longer. The right side, this side here, has a different steric interaction than this side has here. And so because this steric interaction is here, this bond, as I've already tried to draw it, becomes longer, because I want to avoid the repulsion. This bond stays shorter. The shorter a bond is, the stronger it is. The larger the bond is, the weaker it is. And now, of course, the nucleophile will be attacking the weaker bond. And so therefore, we observe attack on this, and we do not observe attack on this one here. Basically, by this principle, a lot of these asymmetric catalysis reactions work, that your chiral information of the ligand is basically desymmetrizing your usually enantiotopic pathways, which should lead to equal amounts of enantiomers, now making a diastereotopic pathway out of this by desymmetrizing simply your symmetrical compound. Again, all this is in the handouts. Have a look at this. I will not ask such type of stereochemical models in the final exam. Nevertheless, this is a very good example to understand the basic principles of asymmetric catalysis. So have a look at this again and keep it in mind. Thanks very much. Tomorrow is another lecture, right? And then 2 tutorials. Thanks very much.